In this video, I'm going to be talking about another approach for event extraction, but we are doing it for biomedical text. So our domain is biomedical text. So I'm going to be focusing on this paper in 2021, a novel joint biomedical event extraction framework via two-level modeling of documents. With the rapid development of information technology, the amount of textual data generated in biomedical field becomes larger and larger. Biomedical event extraction, which is a fundamental information extraction task, has gained a growing interest in biomedical community. Although researchers have proposed various approaches to this task, the performance is still undesirable. For example, less than 70% for a font score. Since previous approaches fail to model biomedical documents effectively. So we propose an end-to-end framework for document-level joint biomedical event extraction. To better capture the complex relationships among contexts in biomedical documents, a two-level modeling approach is introduced for biomedical documents. More specifically, the dependency-based graph convolutional network and a hypergraph are used to model local context and global context in biomedical documents. In addition, a fine-grained interaction mechanism is proposed to model effectively the interaction between local and global contexts to learn better contextualized representations for biomedical event extraction. So you see, this is a biomedical document and the gold event extraction results. Note that the event triggers and arguments are highlighted in red and in blue respectively. So this is mediated is an event trigger. It has some arguments like NRP1 or KDR. So this is an example of nested event. Note that the annotated events and entities are ground truths provided by this, and the dependency parse tree is derived for. You can use a Stanford Core NLP to just get that dependency parsing, or Adel Institute for AI, or a Spacey, or a SciSpace. There are many ways to get that dependency parse very quickly. And so we need a background on hypergraph. It's a basic component in the proposed framework. So we have a finite set of objects and family of subsets, and a hypergraph is able to describe relationships among more than two objects or vertices. So this is the overview of proposed framework. First, for embedding, we augment word embedding as usual with position embedding and entity type embedding, and then we give it to these stacked HAN and layers. And you get dependency-based graph convolution or neural networks. You give it to hypergraph aggregation. And this module repeats itself, different layers. So in each layer, the dependency-based graph convolutional networks is first to capture the local context. Then, given a biomedical document, a hypergraph is constructed to model the global context. So it's not just sentence level. We are doing it for different sentences, so it's at the text level. And the GCN, you know about GCN, I've explained it in my playlist for graph neural networks. So in order to obtain the representations of hyperedges in hypergraph, the representation of each sentence is derived by max pooling layer, which maps the sequence of representations of words to a vector representation of the sentence. Then for each sentence, representations of concepts in the sentence and in the representation of corresponding hyperedge are obtained after this dependency-based graph convolutional networks. A hypergraph is then constructed for the given document, and the global context is modeled by the hypergraph aggregation procedure. In the hypergraph construction, a vertex denotes a concept occurring in biomedical document. So as we discussed, the one concept may occur several times among different sentences in the same document. For each vertex, the index set of connecting hyperedges is denoted by this. And for each index, assume the representation of the context is denoted by V sub I. The representation of each vertex in hypergraph is calculated using this attention mechanism to hyperedges. And you see UI is just a nonlinear transformation of the hyperedge E sub I. And without loss of generality, we assume that J's word in the sentence is the concept with the representation H sub nu in hypergraph. So we update the representation like this. Because first we concatenate it, give it to a linear, and then the nonlinearity activation function. So we give the hypergraph construction using this, because this dependency-based GCN is still local, but the hypergraph aggregation makes it more global because we attend to different parts. And then we have fine-grained interaction. And this is case HANN layer. You can repeat it several times. Then we can use trigger identification and argument detection using these networks. But we do it jointly, we train it jointly. So this is the way that we train jointly using negative likelihood. But we also add a bias term as, and for nested event extraction is more complex than just plain event extraction. And you see the F1 score for different event types. For example, for this event, for different models and different event types. For example, this event for this model is very low. But if you use knowledge base and LSTM, then you have a better F1 score. So if we go to another event type, even it may get worse. And the F1 score is 44. But the proposed model, as you see, if you use k equal to 2, has these scores.